Okay,
Okay,
so we can start.
all right. So thank you very much for inviting me to speak at your seminar. So I prepared a talk in two parts. So the first part is more it aims at students, and in the second part is more technical, and I will speak about some new results revolving around the notion of Morita equivalence of Lie groupoids. So for that, I decided to start with three different situations which arise quite often. So the first one, number one, one usually deals with cochain complexes encoding some information. And usually to see this information, we have to look at the cohomology of the complex. So, and given two complexes, we want to identify them if they have the same cohomology. So one can do that by introducing the notion of quasi-isomorphism of complexes, and quasi-isomorphic complexes have the same cohomology. The second situation is more geometric. So one has a Lie group G acting on a manifold M, and whenever we fix a point X in the manifold, one has a linear map rho, which essentially takes an element of the Lie algebra of G and gives you the infinitesimal generator at the point X. But I want to think of this linear map as a two-term complex, a two-term cochain complex. So I will put the Lie algebra G here in degree -1 and the tangent space at X in degree 0. And all the other terms of the complex are 0. So as for any complex, this has a cohomology. So the cohomology in degree -1 is exactly the isotropy Lie algebra of G, of the action, sorry. And the cohomology in degree 0 gives you the normal direction to the orbit of X. So the cohomology in this case encodes the transverse geometry of the action. And the third situation comes from symplectic geometry. So we start with the manifold M equipped with a group of symmetries. So this group of symmetries lifts to symmetries of the cotangent bundle of the manifold. But this new action is Hamiltonian, so it has a moment map. And assuming that the action is free and proper, one can look at the quotient, the orbit space of the action, and then one can take the cotangent bundle of this quotient. But on the right-hand side, we have a Hamiltonian action, and we can construct Marsden-Weinstein reduction at the 0 level set. And this gives you this Marsden-Weinstein quotient, which is on the right-hand side. And the question is how these two cotangent, the cotangent bundle and the reduction of the cotangent bundle are related. And it turns out that one can understand these three different situations in a unified way by looking at Morita equivalence of Lie groupoids. So the outline of the talk, as I mentioned before, is given in two parts. So in the first one, I will discuss basics on Lie groupoids. And in the second part, I will move to Morita equivalence of Lie groupoids. All right. So a Lie groupoid, shortly, it's a category, small category in which every morphism is invertible. So the space of morphisms, the set of morphisms, I'm going to denote it by G. And any morphism has a domain, which I call it the source of G, which is an object in M, and it has a codomain, which I call it T of G, which is also an object in M. Any object has a canonical automorphism, which is given by the identity. So I denote this map by 1, takes an object in M and gives you the identity morphism. And this map I here is the inversion. So it takes morphism and gives you its inverse. And also this map M, called the multiplication or the composition of morphisms, is well defined whenever the domain and the codomain of two guys coincide, so you can compose them. So these maps satisfy a bunch of conditions, which essentially tells you that M is a product, an associative product with inverse I and unit 1. But I'm going to require that this data is smooth. So G and M are smooth manifolds. And all these maps that appear here are required to be smooth. And in order to make sense of this fiber product as a manifold, we require that both the source and the target maps, S and T, have to be surjective submersions. So the first examples of Lie groupoids are the following. So the first one is given by Lie groups. So in this case, a Lie group is the same as a Lie groupoid with a single object. Manifolds can be seen as Lie groupoids. So the space of objects is precisely the manifold, and there are no morphisms between different points, and you only have the identity automorphism at every point. You can combine the first two examples to produce the third one, which is given by Lie group actions on a manifold. And this gives you the transformation groupoid. So here the source is just the projection to M, and the target is given by the action. And of course, one can figure out how the multiplication is defined and the inverse and blah, blah, blah. Okay, so the next example is given by submersions. So if we start with a submersion between manifolds, submersion Q, one can take the fiber product of M with itself by using Q, which is on the right-hand side. And this turns out to be a groupoid over M, and the source and the target are given by the canonical projections. Another example is given by symmetries of a vector bundle. So if E is a vector bundle over M, one can look at this groupoid called GLE. So objects are points in M, and any arrow G between X and Y is given by a linear isomorphism between their fibers. So this guy is so a group, so Lie groupoid, and it will be important for our talk. So another example is a groupoid that can build out of a two-term cochain complex. So if we start with a linear map, partial from V-1 to V0, so again, I'm going to think of this map as a complex with only two terms, so all the other remaining terms are 0. Then one can cook up a groupoid by taking the direct sum of these two vector spaces, and the space of objects will be V0. So the source map is just the projection, And the target map will be, I don't know if you can see this. Okay. And the target map is given by X plus partial of M. Okay. So in this case, both the space of objects and arrows are vector spaces. The source and target are linear maps. And you can check also that all the other structural maps, inversion, unit, multiplication, and blah, 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 are also linear. So this kind of groupoids are called two-vector spaces. And given a two-vector space, W1 over W0, you can construct a two-term complex by taking V minus 1, the kernel of the source, and partial is given by the restriction of the target to the kernel of the source. Okay, so there is this bridge between two-term complexes and two-vector spaces. So more generally, there is an interesting class of groupoids called VB groupoids, which are groupoids internal to the category of vector bundles. So I write this as a diagram in red. So E is a vector bundle over G, B is a vector bundle over M, but also E has a groupoid structure over B, and G is a groupoid over M. And we require that all the groupoid structural maps, source, target, and blah, 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 are vector bundle morphisms covering the corresponding structural maps of G. So one of the main examples of VB groupoids are given by the tangent groupoid of a Lie groupoid. You have G a groupoid, and you can apply the tangent functor to each of its structural maps. You end up with a VB groupoid called tangent groupoid. And these VB groupoids admit duals, and taking the dual VB groupoid of the tangent groupoid, one gets the cotangent groupoid of a groupoid. So here, A star is the dual of the Lie algebroid of G, and one can describe an explicit groupoid structure on this guy. Well, there are many other examples of Lie groupoids coming from foliation theory, from principal bundles theory, from orbifolds, and many other examples. So, but for the purposes of today, these examples will be enough for us. Okay. Let me tell you about morphisms of Lie groupoids. So since groupoids are categories, one relates categories via functors. So if we start with a groupoid G over M and a groupoid G prime over M prime, Lie groupoid morphism is a smooth functor. So this means that we have two maps at the level of morphisms, which is capital F, and one of the level of objects, which is small f. And capital F takes arrows between objects to arrows between objects, and composition into composition. All right. So if we go back to our examples, one can see that groupoid morphisms between Lie groups are precisely Lie group morphisms. Groupoid morphisms between manifolds are just smooth maps between manifolds. And if we look at groupoid morphisms between transformation groupoids, one recovers the notion of equivariant map. If one has a morphism between a groupoid and the groupoid associated to a vector bundle, to the groupoid of symmetries of the vector bundle. So this gives you a map which takes an arrow G, map delta, which takes an arrow G and associates an arrow in GLB, which is just a linear isomorphism between the fibers. And delta takes composition into composition. So which are these two equations that I wrote here. So such a Lie groupoid morphism is called a Lie groupoid representation. Okay. So associated to this linear action of G on a vector bundle, one can construct a new groupoid called the transformation groupoid. And it turns out that this transformation groupoid is an example of a VB groupoid. Okay. More generally, one can look at Lie groupoid actions. So one has here a groupoid G acting on a manifold N, but we need an extra data, which is given by a map from N to M. And arrows in G acts along the fibers of J. And this action is compatible with the composition. So it's really an action. And as in the case of representations, one can take the transformation groupoid, and this will be a Lie groupoid. And in this case, the projection from this transformation groupoid to G is a Lie groupoid morphism. Oh, yes, here. It's better. It's a Lie groupoid morphism. Okay. So I don't know if there are students in the audience, but I put here an exercise, which is a criterion to recognize actions of Lie groupoids on another manifold. So if you have a groupoid morphism F from a groupoid H to G, such that this map F hat is a diffeomorphism, so not a groupoid isomorphism, it's a diffeomorphism, then one has an action of G on M along this map little f defined as follows. So you take the inverse of f hat that I'm call it sigma. So sigma Gn will be an element in H, and then you apply the target map of H. So this will define an action of G on N along little f. And if you take the transformation groupoid of this action, this guy is isomorphic to H. So whenever you had a morphism of groupoids whose hat map is a diffeomorphism, this immediately tells you that there is an action and the domain of the morphism is the transformation groupoid. So one can apply this exercise to the particular case of VB groupoids. So if we start with a VB groupoid E with projections QE and QB, there is a vector bundle over M, which is very important for in this theory of VB groupoids, which is called the core bundle. And the core bundle is just the kernel of the source of E, which will be a vector bundle over G, and then you pull it back to M by the unit map. This is the core bundle, and this guy fits into an exact sequence of vector bundles over G, which is given by this, the pullback of the core by the target, and the pullback of B by the source on the extremes of the sequence. And in the middle, you have the total space of the VB groupoid. And now you can look at the projection, QE from E to G. This guy is a groupoid morphism. It's a groupoid morphism, and you can look at its hat map. So the hat map will be this in blue. And this map is precisely the arrow from E to the pullback of B by the source in the exact sequence. So this guy will be a diffeomorphism if and only if the core of E is 0. And in particular, this tells you that since the hat map of the projection is a diffeomorphism, then G acts on B, and E has to be isomorphic to the transformation groupoid of the action. So I wrote this in this diagram. So one can choose a section of the hat map and then take the target, and you will get a map from the pullback of B by the source to the pullback of B by the target. And this is precisely the action. But since everything here is linear, this will be actually a representation of G on B. And the conclusion is that VB groupoids over G with trivial core are in one-to-one correspondence with representations of G. And if the core is not 0, one can also associate a representation of the groupoid, but this is a representation in a more flexible way, and this is called a representation up to homotopy. So this is just for you to know that one can also give an answer if the core is not 0. Okay. So here's an exercise again. So suppose that we have a map between two-term complexes. So we have a two-term complex V and a two-term complex V prime, and a cochain map whose components are F-1 and F0. So then you can construct a groupoid map in this way on the right-hand side. And so if this guy is a cochain map, then you can construct a groupoid map. And if you have a groupoid map which is linear, you can obtain a cochain map between the complexes. So this tells you that actually the category of two-term complexes and the category of two vector spaces are equivalent categories. Good. So let me talk about the transverse information encoded by a Lie groupoid. So we start with a Lie groupoid G over M, and we fix a point, an object X in M. So then associated to X, one has the orbit of X, which consists in all points in M, all points Y in M, which can be connected to X by an arrow, by a morphism in G. So this is the orbit space. This actually gives you an equivalence relation in M, and we denote the corresponding space of equivalence classes by M mod G, and this guy is called the orbit space of the groupoid. The other piece of information associated to X is the isotropy group. So these are automorphisms of X in G. So these are arrows whose source is X and its target is S as well. So it's a loop. Well, this guy is a Lie group called the isotropy Lie group. And the isotropy Lie group acts on the normal direction to the orbit, acts linearly on the normal direction. And well, there are many ways to define to see this normal representation. But since I introduced VB groupoids before, maybe I will explain how you can define the normal representation in terms of VB groupoids. So the first thing is that if you take the orbit O of X, you can restrict the groupoid to the orbit. So this is a new groupoid, which is actually a subgroupoid of G. And now you can take the normal bundle of everything. So the normal bundle of the restriction of G, this will be a vector bundle over GO. And you can take the normal bundle of the orbit. This will be a vector bundle over the orbit. And it turns out that this thing is a VB groupoid. And if you compute the core of this guy, the core is 0. So the normal bundle to this restriction is actually a transformation groupoid defined by a representation of GO on the normal bundle of the orbit. And now if you look at how the units act, you will see this normal representation. So in summary, the transverse information encoded by a Lie groupoid is a topological space, which is the orbit space, a bunch of Lie groups, which are the isotropy Lie groups, and a bunch of representations, which are the normal representations. This information is functorial in the sense that if one has a groupoid morphism between a groupoid G and G prime, then one has a continuous map between the orbit spaces. So I denote it by F bar. One has a Lie group morphism between isotropies. And we also have a morphism of representations between the normal representations. And what I want to do is to find a condition on a Lie groupoid morphism, which tells you that all these maps in the red hand side, actually, F bar, F, and this representation morphism are actually isomorphism. So we want a condition on F, which tells you that F bar is a homeomorphism, F is a Lie group morphism, and this map is an isomorphism of representations. So the answer to this question is related to the main topic of the talk, which is the notion of Morita equivalence of Lie groupoids. So I don't know if I should stop here for a break or...
No, in principle, if you plan to talk for 2 times 25 minutes, 2 times 45 minutes, then at some point it is good to have a break. And if it is a natural point for a break, we can do a break.
Yes, I think it's good to stop here for a break, because the second part is going to be more technical, but I don't know if there are questions so far.
Okay, so questions, please feel free to ask. Everybody knows everything? Strange.
Yeah.
Okay, so if there are no questions, I propose that we take a 10 minutes break and we reconvene. It's like 5 minutes to 3 Warsaw time, and we will
Okay.
continue
All right. Okay.
recording, and we can continue.
Okay. Okay, just summarizing. So we have found a bunch of information associated to a Lie groupoid, which we called the transverse information of a groupoid. So it consists of the orbit space, isotropies, and normal representations. We have seen that this information is functorial, and we want to find a condition on a Lie groupoid morphism which tells you that this transverse information is the same. Okay, so this is related to the notion of Morita equivalence of Lie groupoids. So I'm gonna fix a morphism F between G and G prime. So just let me close my window here. From G and G prime. And this morphism is called a Morita map or a Morita morphism. If this diagram here in 1 is a good pullback of manifolds, so this means that G as a manifold is diffeomorphic to the fiber product of G prime with 2 copies of M over 2 copies of M prime. And the second condition is that this map here, the target composed with the projection, is a surjective submersion. So this tells you that condition 1 tells you that if you remember that F is a functor, then condition 1 is exactly something called being fully faithful in category theory. So this means that at the level of morphisms, F induces a bijection. And the second condition tells you that the functor F is essentially surjective. So this means that if you take an object in M prime, this guy is not necessarily in the image of F, but it is isomorphic to someone in the image. So there exists an arrow in G prime, someone in M, and this arrow in G prime connects the image of the guy in M with the guy that you already fixed in M prime, right? So that means being essentially surjective. So the point is that in category theory, okay, so these are the Morita maps. And there is a theorem, very nice theorem by Matias Del Hoyo, which tells you that a morphism between Lie groupoids is a Morita map if and only if it induces an isomorphism between the transverse data. So if we go back to this information here, this guy is a Morita map if and only if F bar is a homeomorphism, F induces a Lie group isomorphism between the isotropies, and an isomorphism between normal representations. So the guys that we were looking for are precisely these Morita maps. Okay, so just a remark about category theory. So in category theory, we identified categories if they are equivalent. So this means that, we will say that phi, a functor between 2 categories C and C prime, is an equivalence if there exists another functor, psi, going into the other direction, such that these compositions are not exactly the identity, but they are naturally isomorphic to the identity. So there is a natural transformation between this guy in the identity and also the other composition. And the classical result in category theory tells you that equivalence of categories are the same as functors which are fully faithful and essentially surjective. So in principle, a Morita map, which is by definition fully faithful and essentially surjective, admits a quasi-inverse. So admits a map going into the other direction and such that the composition is naturally isomorphic to the identity. But the point is that we are working in the smooth setting. So it is not necessarily true that a quasi-inverse of a Morita map is also a smooth map. So because of this, we will formally invert Morita maps, and this is precisely the notion of Morita equivalence. So two groupoids, G and G prime, are called Morita equivalent if there is a third groupoid, H, together with Morita maps to G and a Morita map to G prime. So the way you should think of this is as a kind of map from G to G prime, which first take the inverse of phi and then compose with phi prime. It's a fraction of Morita maps. So in other words, Morita equivalence is the equivalence relation generated by Morita maps. Okay. So there is another description of Morita equivalence of Lie groupoids in terms of something called principal groupoid bibundles. But at least, I mean, for me, this one is more, it's more natural, at least for me, because I like to understand things as functors and equivalences and blah, blah, blah. Okay. So because of this theorem by Deloyo, two groupoids are Morita equivalent if and only if they have isomorphic transverse geometry. And there is a more modern way of saying this, which is the following. So there is a one-to-one correspondence between Lie groupoids up to Morita equivalence and some objects called differentiable stacks up to isomorphism. So if you would like to define or to understand what a differentiable stack is, you have to learn about categories fibered in groupoids and sheaves and Grothendieck topologies and that kind of things, which is super interesting. But the way we think of now a differentiable stack associated to a Lie groupoid is just the isomorphism class of the transverse geometry. So it's a topological space, the orbit space, with some information attached to it, which is given by isotropies and normal representations. Okay. So let me look at an example. So I will back again to the relation between two-term complexes and two vector spaces. So I'm going to take a two-vector space V associated to a two-term complex partial between V-1 to V0. So I wrote down here the formulas for the source and the target maps, just for you to remember. And I will describe the orbit and the isotropies for this groupoid. So if we fix an object V in V0, what is the orbit? So the orbits are all the guys, all the objects, all elements in V0, which are connected to V by an arrow. So an arrow is a couple, MV, and the source of MV has to be V, and the target is V plus partial M. So the orbit of an object V is V plus the image of partial. So it's the equivalent class by taking the quotient by the image. So in other words, the cohomology in degree 0, this complex, which is given by the co-kernel of partial, describes precisely the orbit space of this groupoid. So the cohomology of the complex, at least the degree 0 part, is related to the transfer geometry of this guy. And similarly, an arrow belongs to the isotropy group of V, if and only if this arrow is a loop, which means that V, the source of this guy, has to be equal to the target, which is partial M plus V, which forces M to belong to the kernel of partial, which is precisely the cohomology in degree -1. So the cohomology in degree -1 of the complex encodes the isotropies. Okay. So now, if we want to identify two vector spaces with the same transverse geometry, this is related to identify two-term complexes with the same cohomology. And the exercise here is that a map between two vector spaces is a Morita map if and only if the corresponding cochain map between two-term complexes is a quasi-isomorphism. Okay, so this is related to the first situation that I presented to you at the beginning of the talk. Right, so identifying two-term complexes up to quasi-isomorphism is the same as identifying some groupoids up to Morita equivalence. So here I put some examples for you to check. So if one has two Lie groups, G and G prime, which are Morita equivalent as groupoids, this is the same as saying that these two Lie groups are isomorphic as Lie groups. So, and if you look at manifolds as groupoids, so you see a manifold as a groupoid over itself, and a manifold N as a groupoid over itself, these two groupoids are Morita equivalent if and only if the corresponding manifolds are diffeomorphic. So Morita equivalence in this sense recovers the way we identify Lie groups and we identify manifolds. If you look at now to the transformation groupoid of an action of G on a manifold M and of G on a manifold M prime, being Morita equivalent means that they have essentially isomorphic slice forms. So if you remember the slice theorem, which tells you how is the local structure around an orbit, this is precisely described in terms of the isotropies and the normal representations. And if two groupoids are Morita equivalent, they have isomorphic transfer data, which is what I try to say here in example 3. Another example is that every transitive groupoid, this means that the groupoid has just one orbit, so this guy has to be Morita equivalent to a Lie group. And actually, you can describe a Morita map between them. You take just one of the isotropy groups and take the inclusion to G, and this is a Morita map. So in particular, this gives you Morita equivalence. So now if you, in example 5, if you take a submersion groupoid associated to a submersion from M to N, then this groupoid is Morita equivalent to N, to the unit groupoid of N. Okay. So essentially the transverse information encoded by the submersion groupoid is just the transverse information to the groupoid associated to a manifold, which is just the manifold. Right? The orbit space is the manifold, the isotropies are trivial, and the normal representations are trivial as well. Okay. Good. Okay, so this was what I learned about Morita equivalence a long time ago. And when I was studying this thing, some question came to me because I was working on Dirac structures and that kind of things, and I used a lot Mackenzie theory of VB groupoids. So the question that came to my mind was, okay, we know that Lie groupoids up to Morita equivalence are related to differentiable stacks. So maybe if one looks at Morita equivalence of VB groupoids, one could say something about vector bundles over stacks. So
I have a question. Sorry, before you go on, may I have a question? So does this correspondence lift to the cohomology of the orbit spaces? So if you look at the Bot-Schulman-Stashev cohomologies of the two Morita equivalent groupoids, can you say something about them? I mean, if you think of the BSS cohomology as a model of the cohomology of the orbit space represented by the simplicial nerve, is there some relation then between the two BSS cohomologies?
Yes, I mean the complex of this simplicial nerve, its complexes are quasi-isomorphic, so they have the same cohomology.
Ah, good, because that's a little bit more than just the sort of homeomorphism between the two spaces modeled by the nerves, right? Yeah.
Exactly. Yeah. So I will go into this point in a couple of minutes because I want to show you examples of Morita invariants, and one of the Morita invariants will be precisely the one that you had.
Great, thanks. Okay, thanks.
Good, sure. Okay, so I want to tell you some words about Morita equivalence of VB groupoids. So now we have a VB groupoid E over a groupoid G, and a VB groupoid E prime over a groupoid G prime, and a map between them, a VB groupoid map. So we will say that this map is a VB Morita map if it is a VB groupoid morphism, but it is also Morita. It's a Morita map between the groupoids E and E prime. So it's a Morita map between E and E prime, and this map is linear. That's the point, okay? And there is a theorem that we proved with Matthias Deloyu, which fully characterizes this VB Morita map in terms of information on the base and along the fibers. So a map is VB Morita if the base map between the groupoids G and G prime is a usual Morita map between groupoids. And the point is that these VB groupoids associated to any VB groupoid, there is a two-term complex, which is called the core complex. All right. So this is essentially the same construction that I explained here when you take a two-vector space and produce a two-term complex by taking the kernel of the source and blah, blah, blah. So you can do the same for VB groupoids, but now you have a complex, a two-term complex of vector bundles over M, and this C prime, B prime will be a complex of vector bundles over M prime. These are models for the fibers of the VB groupoid. And this guy is VB Morita if it is Morita on the base and Morita between the fibers, which tells you that these two complexes are quasi-isomorphic. But there is an extra information which that comes from the fact that these two complexes are associated to VB groupoids. These are not only two-term complexes of vector bundles. These two-term complexes of vector bundles come with symmetries. And these symmetries are called representations up to homotopy. So our theorem says that VB Morita maps are the same as being Morita in the base and a quasi-isomorphism of two-term complex with these fancy symmetries. Okay? But anyway, so this is the theorem, and with this theorem we can produce examples. So the first example is this. So I'm going to take a two form on a groupoid G, and I will look at the sharp map of omega. So this map goes from the tangent of G to the cotangent of G. And we will say that this two form is multiplicative if the sharp map is a VB groupoid morphism. Okay? So now I want to characterize the condition of omega sharp being VB Morita.
Sorry, is it the usual notion of multiplicativity as in Kreinig and many others like Burstein and the rest? Yes, is the same. So basically,
Yes.
the graph of what is it? It's in the kernel of the first Dupont operator, right? Of this simplicial nerve.
Exactly. Yeah.
Yeah,
The
okay.
pullback of omega
Yeah.
by multiplication and projections and alternate sum is zero.
Yeah. Okay. Mm-hmm.
It is the same. Yeah. Yeah. So it's equivalent to this map being a groupoid morphism. So now this map is VB Morita if and only if it is Morita in the base, but in the base is the identity, okay, and a quasi-isomorphism between the associated complexes. So the complex associated to the tangent groupoid is called the tangent complex, and this complex is just the anchor map from A to Tm. And the complex associated to the cotangent groupoid is the dual of the anchor. So it goes from T star M to A star. Okay. But this dual, if you take the dual of the tangent complex, this guy is not the complex associated to the cotangent bundle, just because of matter of degree conventions. So you have to shift it by one. So the complexes that appears here in the theorem in the special case of the tangent and the cotangent will be the tangent complex, which is given by the anchor, and the complex given by the dual of the anchor shifted by 1. So I'm going to denote by omega sharp the map induced at the level of complexes. And because of this theorem, omega sharp is VB Morita if and only if this map is a quasi-isomorphism. And now you can figure out whether this map is actually a quasi-isomorphism. If you could try to find more explicit conditions which tells you that this map is a quasi-isomorphism. And these are these conditions on the right-hand side. So the dimension of the groupoid has to be twice the dimension of M. And this kernel here, the intersection of this kernel have to be 0. Okay? All right. So now you can look at you can look at integrability conditions on omega. So if you take the exterior derivative of omega, this is multiplicative also in the sense that you asked me before. And we don't want this form to be closed on the nose. So we want this form to be closed up to a multiplicative 3 form, which is exact in this sense. So I'm going to call this weakly closed. And being weakly closed in terms of the sharp maps means that the sharp map associated to d omega is homotopic to 0. So in terms of complexes, what do we have? We have a 2 form on G, which gives you a quasi-isomorphism between tangent and cotangent. And the derivative gives you something which is not 0, but is homotopic to 0. So this is precisely the notion of one-shifted symplectic stack that appeared in the work of Pantev, Toen, Vaquier, and Vezzosi. So this is the stack structure associated to this information. I think this paper was published in 2013, but 10 years ago, there was a paper by Ping Xu on Morita equivalence of quasi-symplectic groupoids, and another paper by Burschin, Kreinig, Weinstein, and Zhu on the integration of Dirac structures, where they independently found this kind of structures on a groupoid. Multiplicative form with this non-degeneracy, more flexible non-degeneracy condition, and this more flexible integrability condition. But now with this terminology of Morita equivalence of VB groupoids, we realize that actually those structures at the stacky level are precisely these one-shifted symplectic structures. Okay, so now you can reverse arrows and consider quasi-Poisson bivectors on a groupoid. I forgot to put an important word here. This is a multiplicative quasi-Poisson bivector. And the stacky structure encoded by this guy is a one-shifted Poisson stack. So after this point of view of quasi-symplectic groupoids in terms of VB Morita equivalence, some colleagues started to understand other structures in terms of Morita equivalence of VB groupoids. So, for instance, there is this work by Antonio Maglio, Alfonso Tortorella, and Luca Vitaliano on one-shifted contact structures. So they use part of our work to understand these new structures on groupoids, and so these are some examples that one can understand, because of this theorem that we proved. Okay, so now I want to move to Morita invariants. So the slogan is that if you find a Morita invariant, then you actually found a stacky structure. So for instance, as you asked me before about the cohomology of a groupoid, any VB groupoid has a cohomology, which is given exactly by taking this Bott-Schulman and blah, blah, blah. And it turns out that the VB cohomology is Morita invariant. And if you look at now the VB cohomology of the tangent groupoid, this encodes the deformation theory of the groupoid. And in particular, the groupoid deformation cohomology is Morita invariant, which is actually a result by Krajnik, Mestre, and Ivan Strushiner. So they proved this result in a completely different way. And some years after that, we realized that actually deformation cohomology is, the Morita invariance of deformation cohomology is a special case of the Morita invariance of the VB groupoid cohomology. If you look at the category of representations of a groupoid, it is Morita invariant. So, which is compatible with what happens in the algebraic setting. Two associative algebras are Morita equivalent if they have equivalent categories of representations. So for groupoids, the category of representations is Morita invariant. And you can look at the category of VB groupoids over a groupoid G. And it turns out that this category is not Morita invariant. So in this paper with Matthias, we gave an example, a very concrete example of this. But the point is this. So associated to this category of VB groupoids over G, there is something called the derived category of VB groupoids. And the theorem is that if you have a Morita map between groupoids, then the pullback between the derived categories of VB groupoids is an equivalence of categories. So if you take the pullback as a functor between the categories of VB groupoids, this is not essentially surjective. But if you take the derived categories, then this guy is actually an equivalence. And combining our results with previous result by Gracias, Sass, and Mehta, which tells you that looking at VB groupoids is the same as looking at two-term representations up to homotopy. What is really invariant in this case is the derived category of representations up to homotopy. So this is a corollary of this theorem. Okay. And also this theorem, it's interesting because now you can answer the question about what is a vector bundle over a stack. So if a stack is just a Lie groupoid up to Morita equivalence, then a vector bundle over a stack is a VB groupoid up to Morita equivalence. So that's the idea of this theorem. Okay, so let me present other invariants, Morita invariants. So just as vector bundles have its vector space of sections, if you look at the analog of VB groupoids, there is no vector space of sections, but there is a two-vector space of multiplicative sections. And together with James Waldron, we proved that actually this two-vector space of multiplicative sections is Morita invariant. And if you look at vector bundles with additional structure, for instance, the structure of a Lie algebroid, in this groupoid setting, this is called an LA groupoid. So the two-vector space of multiplicative sections is also Morita invariant, and it is an example of two-term L-infinity algebra, which is strict. And more recent work by Daniel Alvarez and Miquel Cueca, they show that actually this multiplicative section gives you example of weak two-term L-infinity algebras. If you consider, instead of LA groupoids, you consider quasi-LA groupoids. And as an example of this result by Alvarez and Cueca, you can look at multiplicative forms on quasi-Poisson groupoids. And this recovers the L-infinity structure introduced by Honlei Lang and her collaborators in maybe 3 years ago. Other type of invariants were described by Matias Deloyo and Rui Fernandez. So when they introduce Riemannian metrics on groupoids. So these are examples of Morita invariants. And there are other notions of Morita equivalence that I want to tell you. So for instance, you can speak about Morita equivalence of quasi-symplectic groupoids, which this notion was introduced by Ping Xu almost 20 years ago. You can speak about Morita equivalence of quasi-Poisson groupoids, which appeared in a paper by Ping Xu and collaborators. And now you can try to find invariants of these structures. So for instance, associated to both of these guys, quasi-symplectic groupoids and quasi-Poisson groupoids, the analog of the algebra of observables is a graded Poisson algebra. So this is part of our work with Gabriel Silvestre and Marco Zambon. Also, you can look at Morita equivalence of multiplicative Courant algebroids. So these VB groupoids can be thought of as multiplicative vector bundles. LA groupoids are multiplicative Lie algebroids. Now, there are interesting examples of multiplicative Courant algebroids. And my PhD student, Emma Kupitra, studied this kind of objects and their Morita invariants. So she's going to defend in March. And also you can, instead of working with groupoids, you can work with higher groupoids. And you can speak about Morita equivalence of higher groupoids and what are the geometric structures on higher groupoids. And this is related with this, for instance, with shifted symplectic structures and that kind of things. Okay, but that is another story. So I will just keep my eye on Lie groupoids for this talk, and I think I will stop here. Thank you very much for your attention.
Thank you very much for your interesting talk. I think that we have learned a lot and we have much to think about, especially there are several exercises. By the way, whoever wants to participate in the next seminars should deliver solutions of exercises before the next meeting.
Okay.
Of course, it's a joke. Are there any questions? Questions, comments, praises, complaints?
Yeah, maybe a comment. So for students, if you are interested in learning more about this, there is a survey by Matias Deloyo. I think it's called Lie groupoids and their differentiable stacks. So there is it's a very nice text. I mean, it has a lot of examples. Is very well written. Yeah, I mean, it's a nice place to learn more about this.
No, sure, it will be very, very useful. If you could maybe on chat write down the title.
Yeah. Let me find chat is here. Matias Deloyo. And I think the paper is Lie groupoids and their differentiable stacks.
Oh, great, wonderful. So now we have a source for further study, and yeah. Okay, thank you very much once more. It was very nice lecture. The seminar for today is finished, and we meet again in a week. There were some disturbances in our calendar. In this summer semester, we will again meet roughly every 2 weeks. However, due to severe weather conditions and whatever, there were changes. Therefore, the next talk will be next week. Of course, the announcement will follow soon. Thank you very much, Chris.
Thank you. Bye-bye.
Bye-bye.